Good afternoon, everyone. Um, Welcome to SIT 319, or for the master students, SIT 744. Not sure why it's not. Okay, I think now you should be able to see my screen, my full screen. Yeah. So welcome to the unit. Welcome to deep learning. So I'll just start off by introducing myself. So I'm the unit chair. My name is Tomin George Kanipanal. And for this unit, at least for the T2 offering of this unit, we'll be splitting the lectures. So the lectures 1 to 6 will be done by myself. And from week 7 onwards, Dr. Bahari Nakisa will be taking the lectures. So to give you a brief introduction of myself, uh, well, as such, I'm not a deep learning person per se. My main focus is on reinforcement learning, but I've been in this space since 2014. I started my PhD in 2014, and since then um, completed my PhD in 2019. And throughout this time, I've also had to work with training deep neural networks and so on. So you can say that I've roughly been in the space for the last 10 odd years. So I'm fairly familiar with deep learning, although it's the first time I'm teaching it. And Dr. Nakisa, I think she also has extensive experience with deep learning. And she also focuses on the human aligned aspects of deep learning and AI in general. So apart from the two of us, so we'll be the ones delivering the lectures. Also, Professor Bare will also be doing the online workshops for you. So the other workshop tutors and markers. So you have Dr. Durgesh Samaria. So you'll be seeing him quite often. I think he is also doing the help hub sessions. So I'll come to that as well. Xiaojuan Cheng is a PhD student. Oh, I have people waiting in the lobby. I don't know. Yeah, I think you should be able to join this directly. Yeah, but anyway. Yeah. So yeah, Xiaojian Cheng is a PhD student who will also be one of your tutors. Kundakar Tasrif Noor will be a tutor based in Geelong. Shinje Lee, again based in Burwood, also a PhD student. And Nisha Kumari is also a PhD student, so she'll mainly be doing the marking and things like that. So you may not see her, but you will definitely interact with her through the assignments and things like that. And as I mentioned, the Help Hub sessions will be conducted by Dr. Durgesh Samaria. So this is a good thing about this unit. You can make use of the Help Hub sessions. There'll be um, if you are stuck with any issues or if you are stuck with any problems, you can of course consult him and ask for solutions. Um, yeah. Um, Coming to the unit schedule, so there have been some changes. So you may see that this schedule is slightly different from what you've seen before. So I would encourage you all to just take a screenshot of this, or I'll of course this these slides will also be available on the unit site. Yeah, so just note that one of these sessions. So I think the Geelong session this used to be on Friday. Now it's currently scheduled on Wednesday. So we just had to do this because this was the only time that was um, feasible for the tutors. Right. So today there are a few workshops. Today later there's one in Geelong, which will be done by Durgesh. One in Burwood, um, done by Xiaojuan. Um, yeah. So just keep note of this, and this is the most updated version of the um, workshops, and yeah, the no changes to the online workshop sessions or the lectures. So the online workshops will be done by Dr. Bari, as I mentioned. and it'll be done on Wednesdays from 4 to 5:50 p.m. Right? And this will be online and it'll be recorded. If you cannot make it to any of the in-person workshops, you don't need to ask for permission. You can attend the online ones. But I highly recommend attending the in-person ones because it'll also give you a chance to interact with your peers. And, I think a lot of the benefits from doing a unit like this comes from discussions with your peers and just exchanging different points of view. So I think if you can attend the in-person ones, please do so. If you cannot, then sure, you can attend the online ones. Regarding the Help Hub sessions, so we've been assigned 4 hours per week for the Help Hub sessions. So 1 hour for SIT 319 and 3 hours per week for SIT 744. So the Help Hub sessions will all be run online and it will be done by Durgesh. And it'll run only from week 2 to week 12. So you won't have any Help Hub sessions during the first week. Also, the first week is just going to be a very gentle introduction into the topic. So there's nothing too critical to worry about in the first week. So it'll be done from week 2 to week 12 and including the break week. So in case you're stuck on one of your assignments or if you have any doubts during that time, you can, of course, attend the Help Hub sessions and get those things rectified, right? Yeah, and also please take note of the room venues or the venues for the different workshops. So I've coded it such that, okay, online is orange, Geelong is green, and Burwood is blue. But just take note of where exactly these classrooms are located because I'm not familiar with especially the Burwood classrooms. But if you have any issues with this, yes, please feel free to message me. Um, any questions with the schedule? Okay. If not, let's move forward. So, yeah, recommended reading. So we will mainly be um, referring to these two books. So one is Deep Learning with Python by Francois Chollet. This is more of how do I say? It's a more of a hands-on kind of approach. Um, I mean, the theory is also there, but I think it's more focused on the implementation aspects and things like that. This is a relatively new book, the one by Bishop, and it's supposed to be quite good. I haven't actually gone through this, but I've heard that it has it has very good illustrations and yeah, and the concepts are explained in a very clear way. So I recommend this. This was recommended by the previous unit chair as well. So yeah, please do refer to this. And I believe there are, I'm not sure how many copies are available in the library, but I think you can also find versions of this online. So if you can get hold of one of those, then yeah, please do. The other prerequisites, of course, okay, there'll be some mathematical background that's expected. So in this unit, we'll mainly be focusing on, we won't focus on, the very modern approaches to deep learning. Although we'll try to cover the basics, the basics are evergreen, so that's going to transfer to even the modern methods. Of course, you need linear algebra. You need a bit of calculus. Any clues why you need linear algebra for deep learning? Anyone?
We have some backtracking algorithms, and to solve those, we need a linear algebra.
Sure. Yeah, that might be a specific case, but I think more in general, the way we represent data for deep learning or yeah, for machine learning in general is through Firstly, we represent. We usually use high dimensional data. So it may be images, it may be audio clips, it may be text-based data. But ultimately, what you want to do is you want to use this high dimensional data and you want to convert them into vectors and matrices. And it's with these vectors and matrices and different ways of manipulating them is one of the processes involved in deep learning. So, and that inherently will have to use linear algebra for that purpose. And calculus, any ideas in general at a very high level? Why do we need calculus for deep learning?
It is important for training the models, like finding the gradients. And
Exactly. Yeah. So yeah, I think you pretty much got it right. So deep learning, if you think about it, is just an optimization technique, you can say. Um, and the optimization is a gradient-based optimization technique. So we need to find the gradients of the objective function, and that's the whole basis of this approach. So, and the gradient, of course, is based on calculus. So this is at a very high level. This is why we need calculus. But I think if you're fairly familiar with the basics of these concepts, you should be okay. If not, I think there's also a refresher coming up next week. So I think you should be good either way. I don't think we'll be using any very difficult to understand concepts or things like that. So this is pretty much a unit for people from all kinds of backgrounds. You don't have to be a deep learning expert to take this unit. It's a fairly gentle introduction to deep learning. Having said that, you do need some familiarity with programming, Python and tools like NumPy, Matplotlib. Um, yeah, sure, you can use Jupyter notebooks, Google Colab. So this is one thing that I wanted to highlight here. So if you haven't already got your Google Colab credits, you should have received an email last week. Um, and if you think you haven't, just check your junk folder as well. You should have received like $100 coupon for GCP. And I think in one of the Help Hub sessions, Durgesh might show you how to use these. And TensorFlow and Keras. Yeah, of course, you can also use PyTorch if you want to, if you really want to, but generally during this unit, we'll be following TensorFlow and Keras. Yeah, so again, you don't need to be an expert programmer. You just need to be familiar with some of the basic tools, right? Yeah, it's nothing very sophisticated, at least for now. Do check your Google Colab, your GCP credits. Just check this email, and if you should have received it. If you're 100% sure you haven't received it, just message me and we'll sort that out. So the unit outline. Yeah, so today's session is going to be a very gentle session. It's just going to be an introduction to deep learning. The next few weeks will go slowly more in detail. Two things over here you notice is you'll have two assignments. So in terms of assessment, you have three things that are due. That is two assignments and one exam. And I will release the first assignment at the end of this week. So I'm still kind of reviewing it, but hopefully by Thursday or Friday, you should be able to see it in on the unit side. So you have like the beginning of week 6 up to the beginning of week 6 to submit that. And assignment 2 will also be released in due course in the next couple of weeks. And yeah, the deadline for that is in week 10. And apart from these, and the weightings for these assignments is the first one is going to hold 25% weightage. And the due date is mentioned here. Second one is going to take 40% weightage, and then you'll also have a final exam which holds 35% weightage. It'll mainly cover things that were covered during the lectures and tutorials, but yeah, nothing. I don't think you'll have any like coding as such. Yeah, so it's yeah, I'll release more details about these about the final exam once we get closer to that. But roughly speaking, it's going to be held between the 7th and 18th of October, which is the examination period. Yeah, so as I mentioned, I'll give you more details in due course. Any questions so far about the assessments or anything about the unit? Okay, we can go ahead. So you'll see that this unit has some overlap with some of the previous units you may have taken. So to be honest, I'm not very familiar with the specific contents of these units, but these I've taken it from last year's offering, and I believe it does have some overlap with some of these units, especially the machine learning one. Yeah, maybe the NLP one as well. I think this is a fairly new unit, but yeah, you'll see some overlap, but of course you'll definitely learn some new skills through this unit. And yeah, so you can use the Teams group for any doubts, discussions. So I've created different channels for different kind of information that you want to share. If you want to share, some interesting piece of news that you came across, you can even do that. If you need to reach out to me, I think a better way to do it would be through email, and just mention your subject. Just make sure that your subject starts with SIT 319 or SIT 744 so that it catches my attention, because I get way too many emails. Yeah, so just make sure that you have these things in the subject. And in case I don't reply within 48 hours, just send me a reminder. I'll try my best to reply to you, but I think this is a fairly large unit, so I'm not sure how many emails I'm going to get. So if you can try to, and only email me if you really have to. If you can sort this out by asking your colleagues, or that will be a better option. As long as, or if it's information that's already been communicated to you, just make sure that everything is. If you want to ask me something, make sure that it already hasn't been announced to you, either through the lectures or through any of the Teams channels. Yeah. So I think that's about it for the introduction to this unit and all the logistics. So just before we get into the details, I just wanted to ask, yeah. So if you can scan this QR code and you can start responding to the survey, just to kind of get to know what your expectations are and what your kind of background is, just to get a better understanding of why you actually want to do this unit. Yeah, if you can start responding to this, I think it should update live. Of course, there might be other reasons as well, but yeah, I just okay. For starters, it's good to see that number 4 is not leading. So I'll just give this about 2 minutes. So the first one, it's a relevant tool that will be needed for jobs. Yes, that's very much a good reason for choosing this unit. I think the basics that you learn from this unit is definitely going to be transferable even to the um, latest versions of models that are out there. It is modeled after the brain, which is fascinating. Yes, it is fascinating, but I have to say that at least the tools that we have, they're not strictly. I would say they're more like cartoon versions of what actually happens in the brain. They're not. They have no biological significance as such. It's just that the people who first came across these, or the people who first proposed these models, they took inspiration from how the brain works. Um, yeah, so you may be slightly disappointed if your reason is number three, but of course you'll see that there are definitely some connections with the biological aspects. You're curious to know how it works. Yes, that's a great reason. I think that's the reason why you should be doing this unit also. Happy to see that number two is quite high, and I'm happy to see that number four is not very high. Yeah. So if you've chosen number four, then I'll try and do my best to make sure that you enjoy this unit, right? Okay, so that's good. And you also have one more poll here. So this is just for me to understand what kind of experience you have with deep learning. Yeah. Okay, so I think most of you have either heard about it or maybe played around with it a little bit. I think that seems to be the majority, which is okay, which is totally fine. You don't need to be an expert. Of course, the 11% who consider themselves experts, I mean, you might find the unit maybe too easy, but I think you'll still probably find some things that are. Hopefully, you'll find some things that are new to you as well. Yeah, yeah. I think the others are all okay. Read about it a little bit. Yeah, that's fine. Okay, I think most of you seem to be fairly new to deep learning, which is totally okay. So I'll try to uh, mold the slides accordingly. So today's session is going to be a very it's going to be a very gentle session. I think it's just okay. Before we start with that, maybe just outline the unit objectives as well. So basically, we want to explain deep learning and its role in data science and AI. Apply deep learning theory to formulate data analytics or AI problems. Design suitable deep learning algorithms for unsupervised and supervised learning problems, and model and implement algorithms for processing structured and unstructured data. So data could be in the form of images, text, videos, or it could be anything. And yeah, program and maintain deep learning models using industry strength software framework. So specifically with industry strength software framework, what I'm referring to is just TensorFlow, Keras, or PyTorch and things like that. But as such, we won't really focus on, or let's put it this way. So you won't need to have access to a very powerful GPU to do this unit. And the reason is because this unit is mainly focused on learning the concepts behind deep learning rather than um, trying to solve some very highly complicated problem. So the idea is that if you are familiar enough with the concepts, you should be able to apply that to difficult problems. It's just about scaling and things like that. Okay. All right. So yeah, with that, let's start with a brief introduction to deep learning. So yeah, of course, what motivates deep learning is the promise of AI. So of course, well, by the way, these are ChatGPT generated images. So we have the promise of conversational agents, which I think saw a huge spike um, when ChatGPT was released. Virtual assistants, self-driving cars, and so on. So we have so many things that are promising, like life-changing technology. And just before continuing, I just wanted to also show you. Sorry, shouldn't be this. Yeah, so I wanted to kind of contrast deep learning with, say, some other method like SVM. So you can see that, so this is just the search for the term deep learning. And I've also just put SVM just to show you a comparison. This is from 2004 to present, and it's looking for worldwide hits for this search term. So you'll see that it was pretty low in popularity, like in the early 2000s, and I think 2012 you might see a small spike here. This is when, or 2012 must be this year. So this is probably when AlexNet was first published, which was a very famous deep learning model, which outperformed the other models during that time. And then slowly started gaining popularity, and you can see that methods like SVM kind of dropped in popularity. You saw a fairly consistent amount of deep learning hits in the late 2015 to 2020, that period. So it was starting to decline, and I think this spike is probably attributed to ChatGPT and transformers in general, the transformer architecture. So this is when the transformer architecture happened, which is what ChatGPT and things like that are based on. And you'll see that after that, it's been going very, it's like one of the most popular topics people are looking at right now. So yeah, just want to show that. Yeah, so as I was mentioning, there are many applications that are promised, many technologies that should make our life a lot easier in the coming few years. And at the center of all this, it is deep learning. Of course, we call this AI or artificial intelligence, but it's a very general term, I would say. So if you ask someone more technical, they would say it's, yeah, sure, it's maybe instead of artificial intelligence, you can say machine learning. So machine learning is kind of a subset of AI. And within machine learning, you have deep learning, which is, if you look at it, it's truly one of the technologies at the core of this whole field of research. And it's something that's been powering this whole field since definitely since the early 2010s, but also since the 1980s. It was a big thing. Also in the 1960s and so. So okay, let's look at the difference between machine learning versus classical programming. So the difference is just that in classical programming, you may have some rules and you may have some data, and with programming, you can get some fixed answers. Whereas with ML, you have some data and answers. So you have some data, correspondingly, you have labels for that data, correct answers for the data. So you can think of the data as something like, let's say, pictures of cats and dogs and, let's say, many different animals. And the answers could be the labels. So this is what we call labels. So the correct answers to the data. For example, if you have a label of dog, your goal is to match the pictures of dogs with the label of dogs. And machine learning generally, it comes up with sort of these fuzzy rules, kind of that can be used to classify data and kind of map data to their different labels, right? And some of the characteristics of ML. So generally, it tends to deal with large and complex data sets. So this is one of the things that that has been somewhat consistent throughout the whole history of deep learning. It's not strictly based on mathematical theory, so it's usually something that is engineered. So people just try things out. They find that they might find that it works, and then other people go and look into why it actually worked, and then they might come up with some theory, and some of those theories may not be very robust. It may only work in certain scenarios, but this is the nature of the field. So people try things, they see what works, they go back, they change things, and yeah, so it's a more of an engineering oriented approach, right? So yeah, like I was saying, you have the input data and labels, and based on this, you might train a model. So the model is basically something that tells you, given some input data, it tells you what the label is. So for example, you give the input as like a picture of a dog, and assuming that you have some label data saying that it's a dog, then the model should be able to predict that the picture is indeed of a dog and not of some other animal. Another necessary component is a performance measure. So once, of course, you train the model based on your input data and labels, but to see how well your model is doing, you need some way of measuring the performance. And if you have some performance measure, basically we use that performance measure to conduct some kind of an adjustment to the model. And this adjustment step is what we call learning, right? So it's a very, learning is a very subjective term, I would say. If you look at it from a mathematical point of view, it's just linear algebra. But the reason we call it learning is like functionally, it looks like it presents itself as something very similar to what animals do. You might try something, then you might change your behavior um, based on whatever outcome you measured, right? Um, yeah. So if you look at all this, the key to deep learning is basically information processing, right? So if you observe a baby or a child playing with their toys, you can say that like they're immediately, or at least after some time, they can distinguish between animate and inanimate objects. They know the similarities between dogs, cats, dogs, or I mean, they can correctly identify different animals, let's say. The colors and shape, even if you show a shape and you show it in different orientations, they're able to identify it. The material properties, they know uh, what water should feel like. They know what um, you know, like a solid block should feel like, and they can also somehow infer the causal link between, for example, if a toy has a speaker and which is activated when you press a button, they sort of figure out that the causal relationship. They figure out that when you press the button, you hear the sound, and the sound is being caused by you pressing the button. So these are actually things that are not well. Some of these things are, of course, we can already do with deep learning, but some of the other things like the causal links and things like that are not very trivial to learn with deep learning. So, but the key idea is that we process information, and it is through this processing of information that we are able to do these kinds of tasks well, right? So, of course, the early researchers, they recognize this. So von Neumann, of course, with his the first computer, ENIAC, yeah, so he built this computer in the hope of processing information, which is which turned out to be, very much in line with what deep learning researchers wanted to do as well. This ENIAC computer was, it was programmed with the patch cables. It was definitely not like the modern computers we have today. But so this is just to kind of show you that there was interest in this direction in information processing back in the 40s also as well. And he said something, it's just a quote from him. Whatever the language of the brain is, it cannot fail to differ considerably from what we consciously and explicitly consider as mathematics. So, from this quote, you can say that there was definitely some interest in modeling the brain or modeling what is happening in the brain. And he probably did recognize that one way to do it is with these information processing machines called computers, right? So let's look at, so this is another experiment. So this was conducted much later, but it kind of demonstrates, some of the things that animals around us can do. So Watanabe was the Japanese researcher. I think, so he conducted some experiments where he put pigeons in this box and showed them images. So this box is called a Skinner box. After, I think it's named after a famous psychologist, Skinner. So he showed the pigeons different images, and specifically what he showed the pigeons was images of paintings of different artists. So this is Van Gogh's Starry Night, and this is one painting by Picasso. So he specifically trained them to identify paintings from different artists. And the surprising thing was, well, may not be very surprising, but he was able to see that pigeons are really able to distinguish, the paintings between Picasso and other artists. And the more interesting thing is that when he showed paintings that the pigeons were not trained on, they were able to actually still identify it fairly correctly. So this shows that the pigeons, they didn't memorize the paintings. They notice some kind of features or some kind of patterns in the paintings or in the artist's work, and that's what they were trying to learn, right? And this was done in 1995. So you have to keep in mind that the computers at that time were not able to do these kinds of tasks very well. So that kind of questioned made us question. Okay, what is the, like, computers are like very fast compared to the human brain. Like it can do more than 2 billion cycles per second, but it still struggles with simple tasks like this. Whereas, these kinds of tasks can be done by a pigeon. And they realized that one of the key benefits of a natural brain is that we have massively parallel processing units. So it's not just one neuron that's doing this. It's a host of neurons that are dedicated towards tasks like this. So that actually inspired the study of neurons themselves. So of course, this was a study in 1995, but I'm saying that so people were already studying neurons back in the early 1900s. So if you look at the neuron, so this is roughly what it looks like. So these are called dendrites, and dendrites are often connected to other neurons. And you have this long body over here called the axon, and over here you have the terminals, right? So initially what people did was they tried to kind of model this neuron. And this is one of the very early models by McCulloch and Pitts, which I'll talk about in the next slide. So they considered the neuron to be some kind of a. So their idea was to basically create a mathematical model of the neuron, and of course they came up with something that resembled the neuron. But yeah, you can argue that it's not very accurate and things like that. But it was a first attempt, right? So the way it worked was you had different weights. Each input was connected to the neuron with a different weight, and then the output produced by the neuron was a function like this. So you basically summed up the weights multiplied by the inputs. So you do that for everything, and then you pass it through something called an activation function, and that was the output of the neuron. And this model actually was quite famous in the 1950s or so. So just to speak a little bit about the people who developed this model. So this was called the McCulloch and Pitts model. So this, so they have a very interesting story. So Warren McCulloch was a professor at the University of Illinois in Chicago. And Walter Pitts was apparently a self-taught genius. You know, he apparently at the age of 12, he wrote letters to Bertrand Russell pointing out mistakes in his published work and things like that. And he left home at the age of 15, and he just wanted to study, although he never registered as a formal student. So he would just go and attend classes and make money by doing menial jobs and things like that. So of course he was around this university system, and Warren McCulloch actually noticed how brilliant this boy was, and he actually almost kind of adopted him, you can say. So Walter Pitts was actually homeless at that time, and McCulloch was really impressed by his brilliance. And he basically took him into his own home, treated him like his own son, and they collaborated on a number of different works. And the model that I showed you earlier was one of the products of their work. They also collaborated and wrote the seminal paper, Logical Catalyst of Ideas Immanent in Nervous Activity. Right? So this was one of the first mathematical models of a neural network. So Walter Pitts, as I mentioned, was a genius, but he had a lot of behavioral problems and things like that. So there was one paper in which, so his whole idea was that he should be able to find a way to model the brain, and that is something that can be done. But there was one problem. There was one paper in which they found that the processing of information was not done fully in the brain. They found that there was some type of frog in which the partial processing of it was done in the eye itself, in the eye of the frog. And they were co-authors on this, but Walter Pitts was actually so upset with this finding that he actually burnt a lot of his unpublished work, and nobody knows what he had come up with. So he was working on something called 3D neural networks, and nobody really knows what exactly that work was. And so this is basically to give you some kind of a bit of history of how these models were initially formed. Then there's Rosenblatt's perceptron. So this was a very famous person actually in the 1960s. So he came up with this kind of electronic device based on a single neuron. And he showed that it was able to classify images, like 20 by 20 images. And this was something that had never been done prior to this. He also came up with a few rules for the perceptron, like how to train the perceptron and things like that. But in 1969, there was Marvin Minsky. He was a big name in deep learning, and I think he recently passed away. But he was one of the first ones to show the fundamental limitations of the perceptron. And just to give you some context, like when Rosenblatt first showed his perceptron model, it gained a lot of attention, and he became very famous actually during the 1960s. And when Minsky showed that perceptrons were limited, it kind of completely obliterated the field of research, I would say. But what they concluded was that the perceptrons were limited in their performance. I'll show you exactly why in the next few slides. But they incorrectly conjectured that the perceptrons, even like because they couldn't solve those simple problems, they were fundamentally limited. So this was actually not true. This problem was actually later on solved with multi-layer perceptrons, but I think this was done. I think coincidentally, Frank Rosenblatt also died in 1969, the same year that that Marvin Minsky uh, published this work. Yeah, so he never had a chance to improve his model. So what the perceptron model is, it's very similar to the model that we showed previously. But his basic idea was that you can basically have learn some kind of a line of separation. So I won't go into too much of the details because the reason I'm sharing this is just for it's solely of historical importance, I would say. So if you look at this kind of a problem, where you have a class of dots with black dots and let's say white dots, one way to separate this is just by drawing a line, right? Drawing a line that separates them. And what he said was, so you can just ignore this activation layer, but if you look at the inputs and the weights, so you can see that this, let's say for now, let's say you just had two inputs, X naught and W, and let's say W naught is 1. So you can see that the output would be in the form of Y equal to MX plus C in that case, right? So it's basically just a line. And he had come up with some kind of certain rules for updating the weights, right? He came up with certain rules for updating the weights, and he said that, okay, as long as we can train the weights and find a correct line, that is enough to solve this kind of a problem. And also one thing to note is that this line is not unique. For example, you can have a line like that, which has the same performance. It has the same classification accuracy as the solid line. You could even have this kind of a line. So it doesn't come up with a unique solution, but it comes up with many solutions, and all of them can be correct solutions. So with this model, he actually showed that we could do a lot. Like as I mentioned, he showed that he was able to classify 20 by 20 images and things like that. So many problems which seemed quite difficult, he was able to actually solve them. But where it actually failed, so you could have infinite combinations of weights that separate the data correctly. So where it actually failed was, so this was one of the results in Marvin Minsky's paper or in his book. So for a problem like the OR gate, right? So if you go back to your maybe your 12th grade or so, or 11th grade maybe, you would remember the OR gate. So the OR gate basically just the OR operation. So if your classification problem is something like this, where you want to separate the zeros from the ones in the output for the OR gate, so these kinds of tasks can be easily done. They can, because you can easily separate the output from this type of output from the other types of output by just drawing a line. And remember that the perceptron basically all it does is it basically draws a line. But for problems like the XOR problem, so the XOR problem, like this is the truth table for the XOR gate. For the XOR problem, you have this kind of an output, right? Now, there is no way you can draw a line to separate the red from the greens, right? So there is no way you can do this with the perceptron, basically. So this was one of the things that he showed. So the XOR problem is a very famous problem in the context of deep learning. It has a big relevance. So Marvin Minsky showed that this kind of problem cannot be solved by the perceptron model, and that actually, as I mentioned, it actually was it heavily negatively affected the field. And his conjecture was that if it cannot solve such a simple problem, how can it solve some of the other real world problems, which are actually much more difficult? So yeah, so this is so he basically showed that the perceptron is only valid, or it can only work when the data is linearly separable. So by linearly separable, I mean if you can draw a line to separate the data, then sure, you can solve it. If you can't draw the line, then you may not be able to solve it. And I mean, this might seem like a very simple result, but um, yeah, so you should also note that data can be linearly separable, but on a higher dimension. So this is just in 2 dimensions. You could have like a 20-dimensional problem in which the data is linearly separable, but when you look at the data as such, you won't realize that it's linearly separable. Yeah, so this was a big blow to deep learning, so which triggered the AI winter, I would say. So yeah, so basically AI winter was kind of triggered by Marvin Minsky's book, or his, Perceptrons in 1969. And there was a lot of funding cuts. So before this, a lot of people were interested in this technology, and it held a lot of promise. There were a lot of funding cuts after this because one of the top people in your own field is saying that this approach, which was at the time very popular, this approach was fundamentally limited. And even though the problem was resolved a few years later, I think it got too much negative publicity and it never really picked up in the next few years. And as a result, there were funding cuts. There were fewer and fewer researchers working on AI and deep learning in particular. And people, shifted their focus to other kinds of approaches like support vector machines, which are more grounded, I would say, which are more explainable, which are not necessarily based on like the human brain or anything like that. Yeah, so these kinds of approaches started getting more traction, and it kind of completely killed deep learning, almost completely killed. Yeah, but a few people still continued working on deep learning. So these are pictures of Jeff Hinton, Yann LeCun, and Joshua Bengio. So these 3 people are considered the godfathers of deep learning because especially Hinton, when all this funding cuts were happening, like he was one of the very few people who continued to work on neural networks during the 80s and 90s. And of course, Yann LeCun and Joshua Bengio joined in later, and they were instrumental in popularizing deep learning. And it's not just these 3 people. Of course, there are so many other important people in the field as well. But yeah, just to kind of give you an example. And another thing happened while AI was in its winter, or deep learning was in its winter. PC gaming started becoming more and more popular, and people started having. I mean, there were more and more powerful GPUs available in the market, and data also became more easily available. Like you had YouTube, you had Wikipedia, and so on. So this actually kind of spurred the next uh, well the next phase of deep learning, I would say, which happened in 2006. So this was mainly triggered by one of the papers, Deep Belief Networks by Jeff Hinton in 2006. So this is what initially triggered it, and then there was AlexNet in 2012, which showed that um, improvements in the ImageNet challenge, which is basically a database of 20,000 different object categories, and the task is to identify the objects correctly. So AlexNet showed a huge improvement, and it used some of the. It was based on deep learning. So this actually got people to, you know, it kind of restored faith in deep learning to a large extent. And ever since, it's been more and more popular. In 2015, there was DeepMind, which showed that you can train agents to play Atari games in a way that's superior to human beings. Yeah? So this was like something that was never seen before, or something that we never thought could be done before. Of course, this also had reinforcement learning, that aspect to it. So it was deep reinforcement learning, which enabled this kind of success. And of course, in 2021, there was GPT, the original paper on, well, transformers, I would say, in general, was published, and ever since it's been accelerating at an increasing pace. Um, Sora is one of the like video generation AIs right now, so it's quite fascinating to see what it's capable of. I think most of you must be familiar with this by now. If not, just Google OpenAI Sora, and you'll see a lot of videos from them. Yeah, so it's a very hot summer right now. It's a time where AI is, especially deep learning, is very, very popular. And yeah, when you guys go out into the job market, it's going to be a very interesting time. Yeah, maybe we can take a short break now. Maybe just a 5-minute break. Right now, the time is what? Sorry, 1:57. Yeah, let's meet at 2:02. Right. Just take a short break, and we'll be back. And if you want to ask anything in between, yeah, sure, feel free to ask. Yeah, in the meanwhile, if anyone wants to ask any questions or make any comments, feel free to do so. Yeah, we'll just start in 2 more minutes. I think we can start now. I think it's almost 2:02. Okay. So yeah, I think now let's look at what actually the problem is in deep learning and some of the fundamental properties of deep learning, right? Um, yeah, so basically deep learning is the reason why it's so useful is because it learns like useful representations or transformations of the input data. So by that, what I mean is, let's say you have a problem where you want to distinguish these three animals. You can see that the it's not just producing the correct output in the end. It's also like learning features in between. So the way deep learning works is you have some input, you have a few hidden layers. They call it hidden layers of neurons, and then you have the output layer. And it's you feed the inputs to the input layer, and you take the output from the output layer. And in between is the magic happens in the hidden layers, right? So that's where the unsupervised learning actually happens. So you'll see that in the hidden layers, often uh, you'll see that it kind of starts learning its own representations of the input. Um, and generally, you see increasingly more complex features. So initially, your initial layers might see just a few lines, and the next layer might see more complicated lines. The other ones, the further ones, will see something like that looks more like your input and so on. Yeah, and you can see that the last one looks pretty much like an elephant, which because of which it's able to classify it as an elephant. Yeah, and one of the other things is it can be used as a sort of coordinate um, changing system, you can say. So this is the same classification problem that we showed earlier with the perceptron. Now, if you think about this, if you just look at the data and just think about intuitively what would be a good coordinate system for this data distribution, provided that you want to separate the good the black dots from the white dots. You can say that, okay, this should be something like this. So deep learning can actually automatically learn some kind of coordinate transformation and and correspondingly a better representation of the data, right? And by this you can very easily say that, okay, if in this coordinate system, if it's greater than, if x is positive, it's black dots, otherwise it's uh, white dots. So like this, it can learn many different kinds of transformations. So there are linear projections, translations, step functions, and so on. But yeah, this is just to kind of let you know what deep learning is capable of. Um, and yeah, it can also be the search for the correct representation. So it's a search for the right way to represent the input data. Um, yeah, so you search within a space of possibilities, which is a hypothesis space, and you transform your search, or you guide your search using something like a feedback signal, which we call the training loss, right? We'll come to these things a bit later, but yeah. So it's basically a multi-stage way to process information, right? Or to learn data representations. Um, and the reason we call it deep is because we have multiple layers of representations, and each layer feeds into the next, right? So that's why it's called a deep. Um that's where the name deep comes from. And the depth of the model is basically the number of layers it has. So in modern architectures, you can have even like the hundreds of layers, and whereas in for simple problems, you typically don't need more than 3 to 4 layers. It's usually 3 layers is more than enough. Um, yeah, so yeah, this is basically what I mean by layer. So you have the input over here. Your input passes through layer one, and if you recall the fundamental idea of perceptrons, where you have the connections that are where each element of the input is weighted by a weight, that actually still holds true. Um, so this is actually how it is represented. So if you have an image like this, the image, of course, is going to be vectorized, and each element of the vector will have a corresponding weight associated with it. So those will form the first layer, and then correspondingly the second layer, third, fourth, and so on. So each layer feeds into the next, and it goes on like this, and until you reach the final output. And when you reach the final output, you have some kind of a performance measure here. And if your performance measure is indicating that you made an error, that error is propagated back to change the weights of the different layers, right? So it actually, this error actually goes back and changes the weights of these layers, and that's what is this is called back propagation. So we'll cover that a bit more in detail during the next session, but just to kind of give you a brief introduction of it. Yeah, so in reality, there's no true connection to biological neurons. It's just the inspiration came from biological neurons, but it's not beyond that. There's no such relevance, right? It's just a mathematical framework, and you can see that can also be used as information distillation. So here you can see this neural network. It's something that's used to process facial images. So you can see that in the initial layers, it identifies um, maybe very low level features like maybe eyebrows or nose or lips and things like that, or even edges, edges of the images. In the next layer, it learns something more, complex, where you can clearly see, the eyes and eyebrows and things like that. And the further layer, you'll see that it looks more like faces. So as you go through the network, you'll see that you can see different ways in which the knowledge is represented. So yeah, so this is just for you to understand how the information is processed and some of the fundamental properties of neural networks. Yeah, it maps inputs to outputs through a sequence of transformations, which are themselves learned from the data. So that is one of the most important things in deep learning. Um, as I mentioned, you have these different layers, and each of these representations is actually learned by itself. Um, so that's one of the main reasons why deep learning is so useful. Because if you think about it in a traditional sense, what you would have is you would have to do some kind of feature engineering, and you have to have some kind of feature extractor, and you extract those features, feed it into whatever um, algorithm you want. But with the neural networks, you don't have to do all that. You can just feed in the inputs directly, and then it identifies features by itself. So that is one of the main advantages of deep neural networks. And layers and weights, as I mentioned. So if you have the inputs coming from this side, you have one layer of weights here, second layer of weights here. And the basic goal of a learning problem is to find the correct set of weights, right? So these weights are it's initialized as just some random numbers in the beginning. And the key is to change these weights in a smart way such that your predictions end up being correct. So of course, the way we know that it's correct is because we have some labeled set of data. And if your predictions match the labels, that means you're doing well. Yeah. So basically, if you want to think of learning, it's just a process of finding the correct values of weights, of the layer weights. And what is a loss function? A loss function is basically something that measures your performance. So once you make predictions, you have access to the true targets, that is the true labels, and you see how much your predictions match your true labels. And that is typically represented as your loss function. Right. Okay, yeah. Yeah, that is something that's represented as your loss function. And yeah, you have a loss score. Now, just measuring your prediction accuracy is not enough. You have to actually use this to change your weights as well. So that's the next step. So, and that whole process is called back propagation, you can say. Yeah, so you take the loss function or your loss score, and then you have some kind of an optimizer. Yeah, an optimizer is just something that uses the loss as feedback to adjust the weights. And this whole process is called back propagation. And the trick over here is, or why back propagation is so powerful is because it correctly estimates how much you should change every weight based on this loss score. So I've just inserted a link over here. So it's just something that I found online, and I thought it did a very good job of showing back propagation. So if you have the time, just try and go through this, and you can. It's also interactive, which is great. So here you can see that. Yeah, so they have some very simple problem in which you can actually set the. Yeah, you can actually train the model. Let's say. Yeah, so this is what the data was, and this is your prediction. So you can stop the training whenever you want. So if you also look at the loss, your loss becomes like very low in the end. If you want to look at a more complex problem, I think you also have this kind of a problem. So initially, this is your estimate, and this is the input to your neural network, and you'll see the weights will change, and the output is taken from here. So the output determines the shape of your curve. So the goal here is to replicate this shape, right? To replicate this curve. And the loss is basically how well, a measure of how well it's replicating that curve. So if you run it over here, you can see that with enough time, you kind of get close to being able to replicate this curve. And you see that the loss gradually, on average, it decreases. So if you have the time, just try and go through this link. I think it's a um, good way to kind of familiarize yourself with backprop. Yeah. Okay. There's a question. Yes, Stephen. Somebody's raised their hands. Uh, you can unmute yourself and ask if you want. Are you able to unmute? Yeah, I'm not sure why. Okay, I'm going to assume that you've raised your hand by mistake then. No, I also see more raised hands.
Yeah, hi, this is Amar here. I just have a
Yeah,
question related
sure. Go
to
ahead.
overfitting. Is it applicable on the concept of deep learning as well?
Definitely, definitely. So, yeah, I didn't want to mention overfitting at this stage, but since you already asked, yeah, it's definitely applicable for deep learning as well. In fact, there are specific methods that you use to prevent overfitting, which we will cover. Some of those methods we will cover in due course.
Yeah, perfect. I just asked this
Yeah,
question because on the previous example, when I saw the loss coming like zero, so
yeah,
I said,
yeah.
okay,
So
that's really that's
yeah,
really maybe overfitting. Yeah,
it's a very relevant question. But yeah, since this is just supposed to be a very
introduction.
gentle introduction, so I just
Yeah,
didn't mention about. Yeah, but yeah, definitely a relevant question.
awesome. Thank you.
Yeah. Any other questions? I think Stephen had a question as well, or maybe not. Yeah. Okay, let's proceed. Yeah, so just coming towards the end of this presentation, yeah, just looking at some of the capabilities of deep learning. So, of course, these categories are going to change very fast. So, near human performance currently is, well, image classification, speech recognition, handwriting transcription, and so on. There have been significant improvements to text to speech conversion, recommendation systems like from Google and Bing and so on. Generative art or generative AI in general has made huge improvements since 2015 or so. Better than humans so far. Well, you could argue that okay, Go playing agents, or let's say, so this is specifically referring to the game of Go. So, so the game of Go is supposed to be a very challenging board game. It's supposed to be much more complicated compared to chess. And in 2017, I believe there was a deep reinforcement learning agent that was uh, pitted against the 19-time world champion in Go, and it beat the world champion 4-1. So this was something quite astonishing for the field because Go is a kind of game where we never thought we would be able to beat humans because it needs things like intuition and it needs very hard to quantify measures to be good at that game. So this was a big landmark for machine learning in general, and specifically for reinforcement learning and for deep learning. Other things that AI is better than at compared to humans, maybe nowadays coding. If you take the average human versus ChatGPT, you can say that maybe ChatGPT is much better, or at least produces neater code. Um, yeah, but as I was saying, like you'll see more of these things moving to the right column in the coming years. But yeah, but so far this is the current state. Uh, yeah, remaining challenges. Dialogue systems should be dialogue systems. Yeah, so believable dialogue systems is one thing. Human level machine translation. You will see that although we have things like ChatGPT, you'll see that it actually does quite poorly if you look at certain languages which have low amount of resources. Um, of course, with languages like English, you have a lot of data and you can easily train your transformers. But in other languages like, let's say, Bengali or Arabic, you may not have that much written resources available to train the models. So you'll see that these GPT-like models, they do quite poorly on those systems as well, on those languages. Yeah, human level natural language understanding. So here is a funny example. So if you, this is from Reddit. Um, So someone looked for a salmon swimming down a river, and this is what AI generated. So well, technically it's right, but this is probably not what the person intended, right? So of course, when you say salmon down a river, we're expecting the fish and not the meat of the fish. Um, yeah, and of course, human level general intelligence, it's still not there. I think um, common sense reasoning is still something of a big hurdle for deep learning models and in general for I would say. So that brings me to Moravec's paradox. So Moravec's paradox is basically the whole idea that like tasks which we humans generally consider to be simple are actually much more difficult for agents to learn or for deep learning systems to learn. So something like a child's puzzle over here, you would say that, oh, this should be very easy, but um, the fact that the pieces can be in different orientations, and identifying the correct orientation to fit the puzzle in the correct location, those kinds of things are uh, typically much more difficult to train than something like training an agent to play chess. So these things are, you would expect the chess kind of task to be much more difficult, but it actually turns out it's the other way around. So typically skills that require sensory motor manipulations, those are considered to be much more difficult to learn for a deep learning agent. Yeah, so this is just what we call Moravec's paradox. And yeah, just to kind of conclude, yeah, I think I have one or two more slides, but so this is so NeurIPS is a very well, it's one of the most prestigious AI conferences out there. And what I did is just to kind of gauge the popularity of like machine learning over the years, uh, I just took the numbers of number of papers submitted to these conferences over the years, and you can see that and the last number over here, 25,000, is a huge jump from even from 2022. Um, and it's actually not exactly 25,000; it's 25,000 and something. So I just entered it as 25. Um, but you can see that it's been growing exponentially, and I think probably since GPT, became a thing, the number of submissions have skyrocketed. So it generally is indicative that the field is doing quite well, because if people have to submit papers, it means somebody is paying them. If somebody is paying them, it means there is funding. And if there are more papers being submitted, there's probably more funding coming into the field. So it's just some kind of preliminary kind of analysis I did. This is just in academia, but if you want to look at industry, you can see this is the stock price of a certain company. Any guesses which one?
OpenAI.
No. So this is actually Nvidia stock price, and they are basically, they basically have a monopoly over the market. So uh, the amount of growth that they've seen in the last few years, I can say that is also one of the key indicators that they're becoming like in general, it's becoming more and more popular. ML, ML and deep learning in general. Yeah. Um, so why is it growing? I think we may have discussed this a bit, but firstly, I mean, mainly three reasons. There's more compute, more data sets, more algorithmic advances. So GPUs, when I say compute, of course, I mean GPUs and TPUs and things like that, which is actually making it much more feasible to do, yeah, to process data. The data sets themselves are growing at an exponential pace. So YouTube, for example, every day, 30 years of video is uploaded. That means 30 years worth of video is uploaded every day. So it's almost like impossible for anyone to actually go through. It's only machines that can possibly go through these. And yeah, you'll see similar trends in Wikipedia, Twitter, Facebook, and so on. And of course, we have so many algorithmic advances happening within deep learning, and this is also uh, one of the main things that is driving the whole field. We have better ways of initializing the weights, better activation functions. We have match normalization. So we'll cover some of these in due course. But yeah, this is just to summarize, um, that the field is growing at an exponential pace. Yeah, I think that's about it. So just to summarize, so deep learning, if you want to remember one thing from this lecture, it's that it learns useful transformations of the input data by updating the weights via the gradient of the loss function. That's the typical mechanism. And in general, deep learning and AI have had many ups and downs in history, and there have been many AI winters in the past. But currently, it's a very hot period for deep learning. Yeah, it's currently very popular, especially following GPT, transformers, and so on. And yeah, you'll probably see much more progress in the very near future. And of course, to make that progress, you will, if you are interested in making or playing a hand at making that process, you will have to first get familiar with the basics, and that's what we'll try to do in this unit. So yeah, I think that's about it. If you have any questions, please feel free to ask. I think I can pause the recording for now. I'll stop the recording.